we're going to start with the first one. So the first one was under basic conditions, okay? So we have, under basic conditions, we're going to have, we've got sodium hydroxide is a source of OH minus. Okay, so we've got a charged nucleophile, so we don't need to do anything to our carbonyl for that to happen because the nucleophile is very strong. There's an area of low electron density in the carbonyl carbon, so that reaction will occur. Okay, so we can attack the carbonyl carbon with our nucleophile, and we've got too many bonds then, so we need to break a bond, so we're going to break the carbon-oxygen double bond. Okay. So we've added an OH group. We've got an O minus now here. And then we're going to use some water to create our final product. Okay, so that's an example of a charged nucleophile attacking an uncharged carbonyl. So we're doing the nucleophilic step first and the electrophilic step second. Now the second one was under acidic conditions. Yeah, so we had HCl and we had some water. So HCl is going to give us a source of H+. Water can be a nucleophile, but it's not a particularly strong one. So water by itself isn't going to attack the carbonyl carbon. It needs something else. Okay? So we have H+. Okay? So we're going to use our H+ to activate our carbonyl carbon. Okay, so the first thing we're going to do is we're going to do the electrophilic first. We're going to add the charge. We're going to add the hydrogen. We're going to add the proton. We're going to end up with our charged carbonyl species. So what that does is it makes the carbon far more electron deficient. It makes it more reactive. So at that point, we can take our nucleophile, which is slightly weaker. It's not formally charged, but because the carbon is now so electron deficient, the reaction can proceed. Now the oxygen in the water has given away its lone pair of electrons. It still keeps hold of one of them, but because it's given one away, it gets a positive charge. And then at this point, we then do our deprotonation. So and we end up with our product. Okay? So in that one, we did the electrophilic step first, then the nucleophilic step. But you can see they are the same mechanisms, it's just the order in which you do them that matters. Okay, so that's that. The last thing, just to throw a little bit of confusion out there, is all of those reactions I showed you could actually be reversible. So what that means is if we go to our nucleophile OH, if we have a base present, for example, which we know we do have in some of these, the base can deprotonate. Okay, so we can use that base. That could actually remove the proton from the oxygen. So the OH bond is polarized again. The hydrogen is electron deficient. You've got a base there which is nucleophilic, so it can pick out that proton if it wanted to. You'd get back to this step here where you have the charged oxygen. Okay, and at this stage you could then reform and get back to your starting point. Because if you remember, what we started with is an uncharged carbonyl and a charged nucleophile. Okay. Of course, the other thing we could do is the other way, in which the nucleophile can be protonated. Okay, so we could protonate our nucleophile, which is just the reverse of what we did at the end of that reaction. And then at this point, we can say, well, the lone pair of electrons can reform the carbonyl bond and the nucleophile can leave. And then finally, we can deprotonate to give us back our carbonyl group. Okay, so they are the reverse reactions to what we've just been looking at. Okay, so this first bit we have deprotonated, we have then used the electrons in the negative charge to reform the carbonyl, and then we've lost the nucleophile. At the bottom, we've protonated the nucleophile because we had some acid present. That nucleophile now has a positive charge, but it doesn't want. The way around that is for the lone pair of electrons from the oxygen to reform the carbonyl double bond, and that allows the nucleophile to leave with the electrons to neutralize the positive charge, and then we deprotonate that oxygen to get back to our carbonyl. Yeah, so they are just the reverse. If you look at it, carbonyl plus acid. So carbonyl plus acid goes to protonated carbonyl. You add the nucleophile, and then you lose proton. So that would be going back that way. So all of those reactions are actually reversible, and that's important because as we move on, we'll start to see that once you do your reaction, you sometimes end up with choices. And what we have to recognize is some of these things are all in equilibrium. So sometimes they move forwards, sometimes they might move backwards. But what we'll see later on is that once they hit a condition within that equilibrium that is favorable for something else to happen, it can do. Okay, so it's just recognizing that all of these things at the moment are reversible. So what you need to take away from this is to be able to tell me why is the carbonyl group reactive. Specifically, why is it the carbon of the carbonyl group that is reactive? And then be able to show me that general mechanism. Be able to say, okay, if I have an acid present, what will happen? Okay, if there's an acid present, we're going to do the electrophilic bit first, then the nucleophilic bit. If there's a base present, we're going to do the nucleophilic attack first, followed by the electrophilic attack. Okay, so you need to get those straight in your head. And what we're going to do in this afternoon is we're going to start looking at specific examples. We're going to look at oxygen, so we're going to look at things like alcohols and water as the nucleophile. Okay.